start, and I'm going to continue with the last part of yesterday. I actually want to go through the individual examples that are on the server to illustrate the probability estimation modeling in the R environment. Whether you would be doing the analysis by hand is unlikely, but it's a good setup for the next step, which is to use the there's a computer program called PeakFQ. It's in version 7.3 as of last November, and it's it's the national standard for flood frequency analysis. It's also an incredibly frustrating program to use, so I want to get things set up before we look at it. Okay, so let's get on with our class. I want to run the examples, so let me get tied into everything. Actually, before share hydro, I also want to, I've updated some of the lessons on the Moodle server, and I'll go through that and show you what they are. I intend to get them all done so that you can at least acknowledge that you sat through my terrible videos, either live or Memorex, and are rewarded for that. It always makes me nervous logging in as administrator on a recorded video because I'm afraid of accidentally typing the password in the user ID and giving everything up because I don't want to change the password. And maybe we're logged in. Sweet. Okay, so lesson 15. '18. 17 is not set yet. 19's not set yet. So if you go to any of the lessons and you get a page that looks like, actually I don't know what it would look like for the student. Let me go ahead and impersonate one. If you get this, there's no point because I haven't set it up yet. But if you if it's like this, you won't get this question. It's asked me to preview it. But so most of the latter lessons will be set up like that. So there's a link to the content and verify that actually works. It goes somewhere, and then just take a look at it and answer the questions. And the following questions are something. They're not all going to be this difficult. I've reviewed the content. I think yes is the correct answer. Yay! And you're done. Most of them actually have a legitimate question, but once you get to that, it logs that you have been present for the lesson. And I apologize for not getting this done sooner. I've got no good excuse, but I can blame it on the internet. Yeah, okay, that's about it. So let's go back to the example. So I'll log into, let's use Portal 3 today. That seems fun. This is my favorite one because the background color is this light blue, and I wish I could replicate that with all the other ones. I don't know how. And in terms of our scripts, okay, so the examples are not here yet, so we'll have to go acquire them. So that is done by going to a web browser, and I'm going to navigate to the course website for lesson 19. Excuse me, 21, rtfmps.com. Teaching. Content repository. Well, actually, this is the first real test if I fix the web server. There goes nothing. Sweet, that was extremely reassuring. Lesson 21. Lesson materials. Okay, excellent. So I'm going to want to download these files, and I'll start with I'll start with examples and then the normal example. So save link as, and we should be able to drop it right into our scripts. And create a new folder. PROD probability models. Hit create, and save the file. I'm going to do this for all the files. Save link as, save the file, save link as, save the file, save link as, save the file. That's an empty file. I need to also get the data for this example, which I think is in data. Yeah, there's the file. Save link as, and we'll just drop it to the same location. All right, so now we have all the tools ready, so we'll go into the probability models section. So let's look at the data. So the data file is not very elaborate. It has years and peak discharges for some location. It's a very simplified data file. When we see the peak FQ data file structure, it literally contains the same information, but it also includes a lot more ancillary content that makes it somewhat difficult to read as a human being. So we'll go through the first examples and see what this script. I have one script that is giving me instructions for how to run the other scripts. That's why we're going to this one. So this is Beargrass Creek examples. And we have prototype functions. The first is a Weibull plotting position function. So what this function does, we wrote it, and it takes the input vector x, sorts it in increasing order, and this first statement here, denom is equal to length x plus 1, is counting how many things are in X, adding value 1 to it, and storing it in a object named denom. And then ranks uses the rank function, which orders the X vector from small to big and then returns that value in the variable named ranks. And then finally we take the sorted ranks, so that will have a value of 1, 2, 3, and so forth, divide it by n plus 1, and return that back to the Weibull plotting position function. So what this is going to do is convert our X vector into a collection of plotting positions and ranked data. And then the next part is the component that changes from probability distribution to probability distribution. So this first one here is going to produce a normal cumulative density function. And this is actually built into the R environment, but I scripted it as a function to illustrate how one would build it for functions that are not part of the R environment. So in this case, we have a function named normal CDF. As input, it's going to take a vector of observations, a value for the mean, and a value for the standard deviation. And it's going to return in the normal cumulative density function a collection of cumulative probabilities versus the values in X, which are our observations. And it doesn't have to sort them. That is implicit in the density function model. Then we go through the activities of reading the data. And then here's some labels that will be used in plotting. And then it goes ahead and produces the output. So let me go ahead and kill that one, kill that one, kill that one. Actually going to kill this example. So the first example that we're going to run is the normal distribution, which we've just shown the setup for. I have them done as separate files. The one Beargrass example, the reason I exited it is I noticed it had stuff like this, but it had not corrected for the actual observations because the script was taken from somewhere else. So this one will actually run it. And see, it does have some plotting set up, so let me make room for the plots. So I think that's big enough for the plots. All right. So when I press run, I think it will go down to line 9. And so now it's loaded in the Weibull plotting position function. Next, we're going to load in the cumulative normal distribution. Next thing we'll do is read in the data. And if we look up here in the environment, we have 31 observations of 2 variables. And if we wanted to see what they look like, we have the year and the peak discharge. We probably need to change these labels. Let's see if a lot. Yeah, I'll leave them be for now because I don't want to break it. Okay, so now we're going to produce an empirical unconditioned distribution of discharge. First, we want to estimate the mean of the data using its ordinary meaning, pun intended. So all we're going to do is we're going to take the mean value of the Q peak, which is contained in the object Q.dv, and then we're going to take the standard deviation that's contained in q.db column qpeak CFS. Then we're going to produce a set of model discharges. And so we're going to specify from 700 to 9,000 in steps of 100. Those are for plotting. And then we're going to have model probabilities, which will be based on the model discharges, mu and sigma. Then we're going to plot the two. I think that was here. U, sigma, model Q, model G. Let's go look at, so the model discharges are 700 up to 9,000 in steps of 1. Now I'm going to plot on the horizontal axis the cumulative probability, and on the vertical axis the model discharge values. So this is a model. This is not the real data yet. And here's what our cumulative distribution function looks like. At 700 cubic feet per second, we have a pretty low value of probability. In fact, it's blocked off by the window manager. So we can get a little bit more. There we go. So 700 has a pretty low cumulative probability. The way to interpret that is the probability of observing an annual peak of 700 cubic feet per second or greater is 98%. 700 cubic feet per second or less is wait, I think I said that backwards. And the probability of seeing, yeah, no, I said it right. And I just had a computer disconnect. What happened? I don't even know if you can hear me right now. I've lost control on the computer. I've completely lost control. That's fun. Yeah, sure. Microsoft's error reporting. Microsoft has detected that it's not making any money. Alright, that was really weird. Sorry about that. I don't know what happened. But it looks like it maintained the connection, which is pretty rare. So let me see if I can reset some things, we'll attempt to do that all over again. I don't even think I'm going to edit that out of the video. All right. Other than completely baffling me, no harm. So let's return to this diagram. The probability of observing a discharge of 700 CFS or less is low. The probability of observing a discharge of, looks like 9,000 cubic feet per second is high, which makes sense because 9,000 is almost the entire universe of observations. But the probability of seeing 9,000 or greater is going to be whatever this probability is subtracted from 1. The probability of seeing 700 or greater is whatever this probability is subtracted from 1. So we can do that in our heads. 700 or greater is going to be 1 minus 0.1, so 99% of the time. And let's pick 2,000 because that we can see. 2,000 or greater is going to be 1 minus 0.7, so that would have a exceedance probability of 30%. And that's what this chart's showing. So to complete it, we'll now go ahead and we're going to drop the original observations onto it. So on the horizontal axis, we're going to use their Weibull plotting positions that we just computed, and the vertical axis will be the observed discharge values from the input file. And there we are. So if we stipulate that the Weibull plotting positions are our estimate of empirical cumulative density, our blue line, which is our model, is it's so-so. It's a little overestimating discharge in this intermediate probability range, and in general, one would think it would do better than that. So we could conclude from this two things. The data are not well explained by a normal distribution parameterized by an ordinary method of moments approach. There's other ways to guess those means and standard deviations. Maximum likelihood estimate probably wouldn't produce anything much different, and it's a lot more scripting. The other thing we can conclude is if we have nothing else to use, we can extrapolate to these high discharge values what the probabilities are, and they're quite small. And that's because we've never seen anything much bigger than 6,000 cubic feet per second in that 31-year period. That doesn't imply that it's impossible that we can't get something up in the 10,000. It just implies that based on the last 31 years of observation, nothing's been close. And at an upper limit, we could apply our hydrologic knowledge and could conceivably estimate the maximum possible discharge you could expect from a watershed based on the drainage area and the most rainfall that could possibly come in. And that's not a data thing, that's actually a thermodynamic calculation. It's elaborate and probably doesn't get done very much, but we can quantify an upper limit of discharge if we have to. As the drainage areas get large, Mississippi Basin large, that ability to quantify an upper limit degrades quickly. So the main value of this demonstration here is that we have a probability density function, and we use the observation data to come up with parameters of that density function, and then I plotted them on the same axis. And by doing that, we can visually evaluate the quality of the probability estimation model. Now, if we were going to make estimates from the model, we would do things like, if I want to know what the 99 percentile discharge is, I would use the oops, wrong keys. I would copy the function, paste it, everything's there, and now I would have to give some discharges. And so let's do 900. So 900 CFS has a cumulative non-exceedance of 0.24, or an exceedance probability of 75%. But if I go to 4,000, we're at 8%. 0.8%. And I'm looking for the 0.01 value. And although this is trial and error, it's not horribly difficult to script a little loop structure that can do this guessing for us. Getting there. Let's run 100 more. Okay, I'll go with that. So a 1% discharge, or the 100-year annual recurrence interval discharge for this particular gauge, based on these observation data, is somewhere around 3,900 cubic feet per second, if the normal distribution is an adequate descriptor of the data. But the prudent analyst, we would want to look at some other probability models, because that's kind of crummy. So let's try log normal. And so I'm just going to go ahead and delete normal. Now we'll run the log normal example, and we'll start everything over and do the same thing. Here's the difference. The log normal cumulative density function, in the case of R that's built in, if we didn't have it, we would actually take the natural logarithms, or the base 10 logarithms, it really doesn't matter, of the x values, fit that to a normal distribution, and then inverse transform it. Here we have the luxury that it's built in. Now the parameter estimation is a little different, because now we are estimating the logs of the observations and the standard deviation of the logs of the observations. And then we proceed the same as before. Produce the model, produce the discharges. So now we're going to plot a blue line. There's the log normal version of it. You see there's a change in curvature up in this region. And now we will plot the Weibull plotting positions. And visually that's quite a bit more satisfying. So the log normal distribution in this case passes through most of the observations quite nicely, with the exception of these three here. And now we can go to estimating the discharge for a particular value. let's scroll down and see what goes on here. So this is actually completely interactive. Cool. So we're going to go ahead and enter a discharge value, and it's going to return the estimated exceedance probability in percent. So the function is called the read value function, right? Yeah. I don't think I have to provide an input. But I do have to use the correct syntax. So now when I run this function, it's going to ask me for a discharge. So let's try something up in here about 6,000 cubic feet per second. And it didn't do anything. That's bizarre. That's because I was running my program wrong. 6,000. So for discharge of 6,000, the estimated exceedance probability is 20%. That doesn't seem right. And let's see why that is. It's doing log normal. We'll just do it the hard way. Okay, the median value is about 1,500. So if I provide 1,500, I should get a probability back of somewhere really close to 0.5. And I get a value of 1. So that's somewhat... Oh, duh. I have the wrong... Okay. So I was guessing that the value of 6,000 and then we want to do 100% of that, so we can express it in percent, because that's a common way of expressing it. So this is going to calculate the exceedance probability of a discharge of 6,000 cubic feet per second based on that blue line. And it should be a small number, like about 0.01 or 0.19. If we go to 7,000, so the 93 percentile is right here. Let's see, let's try about 8,000. 2. So 9,000 CFS is the 100-year annual recurrence interval discharge estimate for this gauge based on these observation data if the underlying distribution model is log normal, which is an okay model in this instance. So let's look at another one. We'll look at the Gumbel distribution next. Don't save. So this one is the Gumbel. Everything else is the same, including broken part down here. So as before, we'll load everything into memory. So there's the Weibull plotting position. In the case of the Gumbel distribution, estimating the moments is a little trickier, so I use some rule of thumb formulas from the probability and statistics literature. It's actually from a book I had in graduate school written by Mood and Graybill. I actually can't remember the title anymore. But it had every imaginable probability distribution that was known to mankind in 1986, tabulated with method of moment rule of thumb estimates. So that's what's being used here. So the mean is the usual meaning. Standard deviation is the usual meaning. But there's an alpha moment, which is the mean times the square root of 6 divided by pi. And there's a beta moment, which turns out to be 0.45 times the standard deviation. And those are used in the Gumbel cumulative density function, which is up above, where alpha and beta are parameters of the distribution. So as before, we'll generate model discharges. In this case, we'll go from 0 to 5,000 and model cumulative density values based on the Gumbel probability density function. And we've already plotted the Weibull plotting positions, so we're going to attempt to pass the model line in the picture. So there's the Gumbel distribution model line. And initially they don't look much different than the normal or the log normal, and that's not surprising because these are all based on a family of distributions called the exponential family. So they're all variations of an exponential distribution. And we'll take a look at my estimator and see if it's actually running. So the read value function is built. We'll put we'll again use 6,000 CFS as our starting point. 6,000 in the case of the Gumbel distribution is actually outside what we have plotted, so it should be a very low event. Okay, we've now estimated its probability. Write the Gumbel model, and then we're going to have its exceedance probability of 6,000 based on the Gumbel distribution is quite small. So the analyst's decision is what distribution to use. Now, fortunately, for national use, they have stipulated that a Pearsonian distribution is used, and one of the Pearsonian distributions is the log Pearson type 3, and I don't actually happen to have the equation written up, but it looks like an exponential distribution with 3 parameters, and So that's what we're going to examine next. Make sure I've got all the examples. Gumbel, log normal, normal. I don't know what that one is. That's probably just a... Oh, and the last one is with a gamma distribution. I didn't name it. So here's the last distribution, which is called the gamma distribution. And it too is actually a member of... the exponential distribution is a special case of a gamma distribution. Gamma distributions they're pointy and then they have real long tails out to the right. So in cumulative space, we get a lot of probability fast and then we have a real long tail out to the right. So let's look at the gamma distribution. So cancel that. Kill the Gumbel example. Now we have the gamma example. We'll go through that the same way. So we load in the information. The density function's loaded in. We read the input file. And now we compute components of the distribution. We compute its mean and its standard deviation, which are called mu and sigma. We compute a value called beta, which is the mean divided by sigma squared. It's the mean over the variance. And then we compute another component called lambda, which is the product of mu and beta. And at that point, we've parameterized the gamma distribution. Produce the model discharges. Compute the model cumulative density values. We'll plot the model. So there's our gamma distribution. It too doesn't look much different than anything else than the other ones. If we were to plot them all in the same plot, we'd be able to tell them apart. We'd see that there's different curves, but they would all look an awful lot alike. Put in our plotting positions, and the gamma distribution is also not a perfect fit, but it's also not a bad one. And from this point, we could go ahead and estimate discharge. So again, we'll use the 6000 CFS as our starting point. And 6,000 cubic feet per second has a pretty high exceedance probability according to the gamma distribution. That doesn't seem right to me. Something went wrong there. Let's do 2,000. Hopefully we get about 0.5 back. I wonder if the plot is bad. Lambda. Oh. Try 1500. I'm looking for the 50th percentile just to be sure that it's plotting correctly. Okay, so that does make sense to me. If we do 2000 is 28% exceedance probability. 3,000 is 9%. 4,000, 2%. We're going to creep up on that 1%. much probability, so that's got to go up. There we go, we'll go with that. So in this case, if the data are described by a gamma density function, then the 100-year annual recurrence interval discharge for this watershed, based on these observations, assuming gamma distributed, is 4,600 cubic feet per second. Because that concludes the examples, and the decision of what distribution to use isn't always left up to you. On certain federal projects, we're mandated. No, not mandated. It's encouraged. I don't know what the policy word is. The policy word that says you can use anything you want, but if you don't use log Pearson type 3, we're going to really take a microscope and look in places that you haven't thought about. So most agencies and hydrologists may choose their own, but they'll also do a log Pearson type 3. Ironically, I don't actually have that scripted up in R right now, but we have another tool available to us, and let me see, don't save, called peakFQ. And currently, so this is the worst piece of software on the shared server. In fact, it's the reason that these lessons are coming late in the session, is just getting this to run was a nightmare. So I'm going to first launch peakFQ, and I hope I've left some files there, because if I haven't, I'm in a bad way. So there's the peakFQ interface. Okay, so it looks okay at this point. When we run it in the shared environment, it's going to produce a couple of errors, and I want to show you what those are, because they have to be ignored, but you have to know which ones to ignore. If you're to download peakFQ from the USGS website, and you have a computer that's running the Windows 10 operating system, and you install it as directed, you have a high probability of it actually working correctly. If you install it in any other environment, like I have here, certain aspects don't work right. So to run it, you have to open a file that has input prepared, and I don't think I have any. Okay, so let me cancel that for the time being. I'll just leave that open. The interface looks graphical, but it's really not. You have to open a file, and then we'll use these tab options to set up some information about that file. So I want to see if I actually have an example file already prepared. Which would be lesson 22, which I don't think is uploaded. That might be a short lesson today. We might be almost done. Routing. Should be one that says old lesson 6. Oh, I've deceived myself. Oh, well, okay. We'll prepare the peakFQ lesson offline, and I'll send you a video, because all I'll illustrate is what the data files look like. And I thought I had prepared that ahead of time, but obviously I've not. I have not. That's kind of embarrassing. Okay, well then that's about all I want to go through today, is what we're going to pick up tomorrow is I'll have the files prepared for the PeakFQ application. That's frustrating that they're not there already. That's my mistake. I'm going to look one other possible place. I may have them in the developers portal and didn't remember. Either way, if they're here, I have to get them moved to a place where you all can look at them. Swim R Heck HMS Engage. I regret that, aren't I? Home. Developer. Yeah, I don't have the files on the server yet. So my mistake. I'll get that corrected by tomorrow. In the meantime, I'll work on exercise set 3. If you are inclined, go onto the Moodle server and run through any lessons you haven't run through that have a quiz question so that it logs your attempt. And that's it. So if there's no questions, I'll go ahead and end the session for today. And as usual, I'll wait a few seconds for anyone that wants to ask questions. And if not, thank you for your attention. And I will see you tomorrow, same time, same place. Have a great day. It's beautiful weather here in Lubbock, and I hope that's the same wherever else any of y'all are. So with that, I will end the meeting for today. Thank you very much for your patience and attention. Goodbye. Okay, PeakFQ.